Alright everybody, welcome to a new problem from the backtracking chapter. This problem is called n queens placement and it is a little bit harder than the other ones, but trust me, after solving it, we are going to boost a lot our backtracking skills. So, let's read the statement together because there are a couple of things that need to be explained here. Given a positive integer n, we have to write a program which returns all distinct non-attacking placements of n queens on a n crossed n chessboard. So, we are given the integer n. For this example, n equals 4. So basically, we have a chessboard of 4 rows and 4 columns. And we need to place exactly n queens, right? This is a thing that I'm going to explain. Why does the problem ask us to place exactly n queens? I mean, there are n squared total cells in this chessboard, so why didn't it say like n plus 1, n plus 2, or some other number m? Why exactly n? We are going to see. And also, we need to explain first, what does a non-attacking placement mean? Well, if you've played chess before, I did, I was terrible at it, but at least I know the rules. I know that when we place a queen somewhere on this chessboard, I don't know, let's say I'm going to place the queen here, right? This queen is going to attack a couple of other cells. So, the rule says that when you have a queen placed somewhere, this queen is going to attack each and every cell on the same column, right? So, it is going to attack these cells, each and every cell on the same row, so also going to attack these cells, and also it will attack each and every cell on the two diagonals, right? So the first diagonal is this one, right? Moving up right, and also moving down left. And the other one is moving up left, and this is the only cell, and up right. So take a look at this. One single queen here actually attacks this many cells, right? So this is what non-attacking placement means. You need to place your queens such that they won't attack each other. For example, if I have my queen here, obviously I only have this 3 cells. I don't know, let's see, I'm gonna place also a queen here, and this will attack also this cell. Now, what can I do is place another queen here, and this is gonna attack the other cell. And if I wanna place the 4th queen, I have no other free cell to place it on. So, this state is invalid, and I need, of course, to make some... Oh, also sorry about this. I now realize that when I place this queen, also this cell is going to be attacked. So anyways, I could have placed it here, but you got the idea. No 4th queen for this example. So, knowing now this, let's take a look at our examples and also explain what the output should be. As you can see, for n equals 4, our output is an array of arrays, and each array, as you can see, consists only of integers. So this could be a little bit confusing, right? Because a queen should be determined by its cell, and the cell is determined by 2 integers, the row and the column, right? So what does this 1302 mean? How can we interpret this array as a placement? And here is how. As you can see, let me just erase this a little bit. All right, we have this array, right? This is position 0, position 1, position 2, position 3. So how we are going to interpret this is that these numbers are actually the columns of the queen that will be placed on that specific row, right? The row is given by the index. So the element on index 0 is 1. So the first queen is on row 0 and column 1. And here it is. The next queen is on row 1 and column 3. And here it is. The next one, row 2, column 0. Here it is. And row 3, column 2. Here it is. As you can see, no queen attacks other one, right? This one will attack only these cells. This one will attack only these cells. This one, these cells. And this one, finally, these cells. So this state is valid. Now, for the other one, let's also see what it means, and then I'm going to explain why we only return arrays. 0, 2, 0, 2, 1, 0, 1, 0, 2, 3, 2, 3, and also 3, 1, right? And you can see no queen attacks other one. So again, the question is, why do I have to return arrays, and why do I also return them this way? Well, this is based on a very simple observation, right? And that observation is the following one. Think about this. If I place a queen on some row, right? So for example, how I place this queen on this row. One thing we know for sure is that I'm not gonna have any other queen on the same row, right? So the first observation is that there will be at most one queen on each row. Think about it. How could I have two queens on the same row? They will definitely attack each other. All right, cool. Now, other observation is that I would also not have two queens on the same column, right? Let's say I have this column 2, right? If I place one queen, doesn't matter in which cell, let's say this cell, right? It will attack the other cells of the same column. So at most one queen per row and at most one queen per column. And because the problem asks us to place n queens, let's also explain why this n, right? I mean, the number could have been definitely less than n. It could have asked us to, I don't know, place n-1 queens, n-2, n-3. That would have been possible. But greater than n, it's never possible, right? And this is based on the observations we just made, because if I can place at most one queen on each row, and I have a total of n rows, obviously I won't be able to place more than n queens in total, right? So this is why the problem chose the maximum number of queens that could be actually placed, which is n. And again, let's take a look at the output. Now everything makes sense, right? We basically, as I said, return the columns of the queens that are placed on the row given by the index of that element. And also, based on the second observation, that there are no two queens on the same column, as you can see, these numbers are distinct, right? So each array from the output is actually a permutation of the set 0, 1, 2, n-1. Awesome. Now that we really understood what the output is and what the problem asks us, let's jump into the solution. Alright, so as we have seen, each valid placement is defined by a permutation of the numbers 0, 1, 2, n-1. But this is not true in reverse. Not each permutation of these numbers is actually a valid solution, right? And the simplest example is the permutation 0, 1, 2, 3. If I had 0, 1, 2, 3, this means that this is how I place my queens, which is obviously not a valid solution. So, one way of thinking about this is that I need to generate each permutation, right? And also make sure that it is valid. So, let's write together our 3 key points of this backtracking approach. We have first the decisions, and our decisions should be for each different row to pick the column of the queen on that row, right? So I will go through the rows, right, from 0 to n-1 and pick a number in the range that starts at 0 all the way to n-1. So my decisions is to pick each value column of I, right, in the range 0, 1, and so on and so forth, n-1. Awesome. Now, the decisions are obviously not enough. We still have some constraints, right? The constraints are that no two queens should be on the same row. And this is obviously satisfied, right? Because we go through each row and only choose one column, so one queen to be placed on that row. So we have the row constraint. Let me just put it like this. Row of I has to be different than the row of J, right? For every two queens I and J. And this is satisfied. Then we have the next constraint, which is that no two queens should be placed on the same column, right? So also I'm going to have call of I has to be different than call of J for every two queens I and J. Now, in order to satisfy this, I have to make sure that I generate permutations, right? So I have to make sure that no two elements are equal, and we know how to do that. We've already done it in the generate permutations problem. And also, there is one more constraint. And that one is, of course, the diagonals, right? I've showed you the example 0, 1, 2, 3, which satisfies the first two conditions, but not the conditions of the diagonals, right? So I'm going to write, let's say, no two queens on the same diagonal. All right. And this is a little bit trickier to satisfy. I mean, we have to come up with a way of checking if two queens are first on the same diagonal. We are going to see that in a minute. Let's also write our end goal, because these are all the three constraints that we need to satisfy. Our end goal is actually really simple, and that is, of course, getting all the n queens on their place, right? And the placement to be a valid one. Okay, cool. So let's first see how to check this constraint, because we need to be able to make the check on spot. When we want to place a queen on our current row, we need to be able to see if we have another queen that will attack us on diagonal. And if we know how to do that, basically the problem is solved, right? All right, so I have chosen a 5x5 chessboard for our example. Let's say that we have gone through all these rows from 0 to 3, and we have basically chosen some queens on these 4 rows. Now our current row is row number 5, and we need to place a queen here, right? Let's see how to check only using the values of the rows and columns, right? So without building this matrix and actually iterating through it to see if we have an element, let's just use the array of columns that we will always have in order to store the columns that we have just chosen, right? How we can use that to check if one queen that I want to place on our current row will be attacking any other queen that I've placed before or not. And let's say I want to choose, for this example, this queen, right? If I was to choose this queen, let's see what are the cells that will be attacked by this queen diagonally, right? These ones, and also these ones. Awesome. Let's see if we can find out a relation between them. Let's look at it this way. This is row 4 and column 2, right? Now, the cells that I am going to attack, of course, first of all, are only going to be on rows that are smaller than mine, because I haven't actually placed any queen here on row 5 or 6 if I had them. So I only need to check for the queens above myself. And if, let's say, I'm at row 4 and column 2, the first set of cells that I'm going to attack are the ones that always get decreased by 1. The row gets decremented and the column gets decremented, right? So from 4, 2, right, I am going to attack the cell 3, 1, so 4 decremented, 2 decremented, and also the cell 2, 0, right, which is this one. Okay, awesome. Now, let's see about this diagonal. Here, the row gets decremented, but the column gets incremented this time, right? So the cell 4, 2 is also going to attack this set of cells. Decremented, incremented. Free, free. Decremented, incremented, 2, 4. Awesome. Now, can we figure out a formula, a relation between our cell and the cells attacked by it, only using the rows and columns of them? And we can. Take a look at this. If I'm on row 4, the cells that I'm going to attack on the row above me, so on row 3, are only the ones col -1 and col +1. Okay, so if the difference of the rows was 1 from 4 to 3, for the cells that I attack, the difference between my column and theirs is also 1. The absolute difference, right? Is -1 or +1, but the absolute difference. Cool. Now, let's go 2 rows above. If the difference between the rows is 2, 4 minus 2, the absolute difference of my column, where I place the queen, and the cells that are going to be attacked on that row is also 2, right? So, if I want to place a cell on the row, and the column col, this cell is going to attack each and every other cell, right? Which is, let's say, row prime, col prime, such that the absolute difference between row minus row prime is equal to the absolute difference between col and col prime. And this is the relation we need to check in order to see if some of the cells that we previously placed are attacked by this one on diagonal. Also, I need to check if they are attacked on the column, right? So, the cell row prime col prime is going to be attacked on the column by the cell row col, if of course col prime equals col, right? So, or here col prime equals col. And this is the only two things that we need to check. Now we have found a way of satisfying the constraints on the spot. So when I try to place on my current row a queen on column col, I can iterate through each and every queen that I've previously placed, right? So all the I-1 queens, if let's say all the I queens, if I'm on the row I, and just check if none of these two happen. And if none of these two happen, this means that my queen won't attack that specific queen. If for all the queens, all the I queens, none of these two happens, this means that I can definitely place a queen there. It's going to be fine. No queen that is placed at this point is going to attack another one, and I can move on to the next row and see what I place there. Awesome. So we know how to make the decisions, right? Iterate through each row and try out each and every column from 0 to n-1. We know how to satisfy the constraints. When we try out each column for my current row, I'm going to iterate through the previous rows. I'm going to see what queen is placed there, and I'm going to check if none of these two happens. Awesome. I also know my end goal when, of course, I reach the row n, which in this example is 5. So I basically finished placing the queens on each of the rows. Then I definitely have a valid solution, and I'm going to push it into the answer. So it looks like we have come up with a backtracking approach for this problem. Let's see the code. Alright, so here is our algorithm. As you can see, the first thing I do is that I declare a placement, right? Which is the array that is going to hold us each and every non-attacking placement. So this is why I'm going to return it at the end. I'm using a placement array, which is also initially empty for the current placement. So this is an array of integers, and this is an array of arrays of integers, right? Now, my backtracking function has two arguments, which are the row and the current placement. And first of all, I check if I hit the stopping point. So if row equals n, This means that I've set each and every column value for each and every row. And obviously, because I am checking every time I place a queen, I am checking if the configuration is valid. I am going to always end up here in the stopping point with a valid placement. So all I have to do is just push it into the placements array. Else, what I have to do is that I have to make a decision, right? And that decision means what is going to be the column of the queen that will be placed on the row, right? So this column obviously could be anything between 0 and then -1, and I have to try each and every value, right? So I'm going to try out each and every value for the column, and then I'm going to check if this cell, this column, right, where I want to place the queen on row is valid. This function is going to return a boolean, and it is going to check if for the current placement, which means for the first row queens that I have placed on the first row columns, if I were to place this queen on row and column call, will it attack or be attacked by any of the other queens that I've already placed? And if this is true, this means that the configuration is valid, so I can place that queen. So this is what I'm going to do, right? I'm going to push the value call to the placement array. Then I'm going to continue the search, so call backtracking, right? In order to place the other queens on the next rows and get all the possible answers for that. And after finishing this, as you can see, I am popping the value call out of the placement, right? This is super interesting. And let me take a quick example to really show you why I do that. Let's say this is the columns array, right? And okay, let's say this is row, my current row, right? So what I've done is that I've set each and every value of the columns. I set C0, C1, C2, and now I need to set each possible value for this row. Let's say at some point, right, I set this value to be equal to call, and call is actually a valid one. What I do next is that I call the backtracking function for row +1. So basically I'm searching for each and every non-attacking placement that has the first row +1 queens set on those cells. After I finish that, I am going to backtrack back to this point, right? And because I finished my job with the value call, I'm going to try the next one, call +1, right? So what's going to happen is that if I don't pop this value call, the next value call +1, let's suppose it's also valid, is going to be placed after this one. And the next one, call +2, is going to be placed after this one, right? When in fact, what I wanted to do is just change this value to call +1 or call +2 and so on and so forth. So be very careful after making a decision, right? And finding all the answers for that specific decision, make sure to undo the decision before you make the next one, right? So in order to undo it, we will have to pop that value, and after we popped it and we go to the next column, this element is going to be basically replaced with the next column. Awesome. This is what we do. And after having defined the function, all we need to do here is just call backtracking of 0 and placement, right, which is initially empty, and then return the array of placements that we have just obtained. Cool. Now, let's see how to implement the function isValid. Alright guys, and here it is, the function isValid. Super simple. We have the array of columns, right, for the queens that we have placed by now, and we have the row and the column of the queen that we are trying to place. Now, as I said, I'm going to iterate through each and every element from the placement array, so through each and every queen that I've placed. And as we know, the queen I has a row equal to I and the column equal to placement of I. So I know the row and the column of this queen, so I can check our constraints. I first check if placement of I equals call, which means that that queen is on the same column with the queen that I'm trying to place now. So I'm going to return false if that happens, right? That's not a valid configuration. Or I check if they attack each other on diagonal. and I check if the absolute difference of row minus I equals the absolute difference of call minus placement of I. If for any of these queens something like this happens, I'm going to return false. When the for loop finishes execution, if I reach this point, this means that I have basically gone through each and every queen and I've never returned false, because if I did, I would be out of the function, right? So when I reach this point, I can safely say that this queen won't attack any other queen that I placed in the past, so I can return true. And this is it. Now, what do you think is the time complexity of this function? Well, as you can see, returns are constants. This if statements, which make only absolute differences and check for equality, are of course constant. And we have the for loop, which unfortunately makes a total of row iterations, right? And yeah, of course, it depends on the row. The row could be, of course, 0, which means it returns true straight away. The row could be 1, could be 2. The number of iterations really depends on row. So I can say that the time complexity of this function is big O of row, right? Now, of course, row could be as big as n, so it's technically a big O of n, but let's be precise and write big O of row, and go back to the backtracking function and see how many operations that function does, right? All right, I'm back with the backtracking function. Now, what happens here? If statement checks for equality constant, pushing an element, it pushes its pointer constant. In the else statement, what do I do here? Well, this is interesting. I'm trying out each and every column from 0 to n minus 1. So I do here a total of n iterations, right? Then I check the isValid function, which you can remember it does a total of row iterations. And then this is constant. Calling the function is just constant. We don't care what happens inside the function. It's a different function call. Popping it is constant. And yeah, what do I do is that I call the parent. I make the first and the parent function call, which is backtracking of 0 and placement. So as you know, what I'm going to do here in order to get the total time complexity of this algorithm is count for how many times the backtracking function has been called, and also multiply that by the number of operations it does. So for the number of operations, as you can see, all that's important here is this for loop, n iterations, and the isValid function row iterations. Now, as I said, row could be 0, 1, 2, all the way to n minus 1. So yeah, we have basically two possible options. We either write each value of row and make a Gauss sum out of that, but the simplest one, and actually a legit upper bound for this, is just suppose that this is almost n, right? So our backtracking function, only one function call, right, will be performing in big O of n squared. Okay, awesome. Now all I need to do is count how many different function calls will be performed starting from the parent one and until we found out each and every possible solution. Now, in order to do that, what I'm going to do, of course, I'm going to take each solution and count how many function calls did I need in order to get to that solution, right? So this is again pretty simple. Let's take one solution for the previous example. Let's take 1302, right? So this was a solution, 1302. Now, in order to get a solution like this, what do? I start with the parent function call, which is for row 0 and the empty array. Then, of course, my first column should be 1. So I'm going to have call equals 1 is going to be valid. I'm going to push 1 and I'm going to call the backtracking for row plus 1 and our new array, right? Then guess what? Of course, I'm going to, inside this function call, I'm going to have call equals 3 and push a 3 in order to get that solution, and then call backtracking for row equals 2 and 1, 3, right? Then, of course, I'm going to push the 0. So 3, 1, 3, 0. And then, of course, I'm going to push the last element, which is 2, and I get to 4, 1, 3, 0, 2, and this is obviously the stopping point, right, as the row became equal to n. So as you can see, as expected, I needed 4 other different function calls just to get a solution, right? And again, this is obvious because we start with an empty array, and for each different function call, we just pushed another element in that array. So in order to get a solution, right, on an n crossed n chessboard, right, so for the general case n, I need n different function calls. So the total number of function calls is how many different solutions are there crossed n. And this is the problem. We actually don't have a formula now for the total number of solutions because it's actually pretty hard to compute it, or maybe there is some formula, some mathematical formula, I don't know. If it is, I'm sure it's like going to be a paper about it because it's not so easy to come up with one. So we are going to also take an upper bound for the number of solutions. Again, each solution is a permutation of the number 0, 1, 2, ... n minus 1. So what I can say is that the number of solutions will be less than or equal to the number of permutations of those n elements, which we know there are n factorial permutations consisting of n numbers. So n factorial crossed n, because we need n different function calls to get each of the solution, and also crossed the time it takes the function to run. So we're going to end up with a time complexity of big O of n factorial crossed n cube. I know it's a very slow approach. There is actually one way to reduce one n and make it n factorial crossed n squared, and we can talk about that, but this is not the point here. The point is to really understand how to solve more and more complex backtracking problems like this one. Alright guys, as always, enjoy coding. This was Andy. I'm gonna see you on the next one. Bye.